In the last video, we have completed the fixed bias configuration. Today we are going to see the emitter bias configuration. So similar to the fixed bias configuration, here the circuit diagram for emitter bias configuration is same as the fixed bias, but only a addition of Re, that is a emitter resistance. Okay, why this emitter resistance is added? It is added to increase the stability of the configuration. Stability means, as I told in the last class, there are some factors like beta DC and ICEO, that is common emitter current gain and collected to emitter with base open. These two factors, these depend upon temperature. Okay, so as my temperature increases or changes, these two factors came into picture, and because of that my characteristic will change. So it means my circuit is not stable. So that's why I have improved my circuit by just a addition of Re. Okay, by addition of this resistor in the emitter circuit, we are going to increase the stability. So the emitter Re connected with the emitter to improve the stability over the fixed bias. The more it will become stable means it will depend on temperature less value, means as the temperature will change, it will not change that much, that is means it is more stable. Okay, this is the emitter bias circuit. Similar to the previous one, fixed bias, here also both AC and DC part are there, but here we are only dealing with the DC components, means we have to open circuit the capacitor, we have to make zero for this in AC voltages. So I have not drawn that circuit, but you will do. Just remove these two capacitors like the previous one, and only this small portion will be left: VCC, RB, RC, BJT, and RE. Okay. So here also, like in fixed bias, here also four points that we are going to read. One is input loop. So here the input loop is between base and emitter. So that is called base emitter loop. Second one is the between collector and emitter. So that is called output loop or collector emitter loop. And third one we will see the saturation level. And then next we will see load line analysis. Okay, for each configuration we will see these 4 points. So let's start for the first from the emitter base loop. So what we are going to do, we will see the emitter base loop. It looks like a VCC, RB, a BJT across which a voltage of VBE and a RE, that is a emitter resistor is connected. Okay, so here also VCC, RB, a BJT across which a VBE is there between base and emitter, and a RE is connected. It looks like a closed loop. So if I write a KVL, Kirchhoff's voltage law, then what it will become? It will become VCC starting from here. I am moving from here like this. So negative to positive means plus VCC. Then a current IB is flowing. A current IB is flowing through RB. That means IB RB. Why minus? Because across a resistor voltage decreases positive to negative. So IB RB. Then plus to minus, that is minus VBE. Then again across the emitter a current IE is flowing. That means minus IE RE equal to 0. Okay. And if you remember in our previous videos, we have seen our IE which is nothing but beta plus 1 IB. Okay, how we know our IC, that is equal to beta IB, IC, that is equal to alpha IE. Okay, so in place of alpha, if I will write beta upon 1 plus beta like this is the alpha value IE. So if I will convert my IE in terms of IB, then I have to replace this beta IB in terms of IC. So if I will change my IE in terms of IB, because here what we know the value of IB. Here we can find the value of IB, so that I can change my IE into IB. So IE, it will become beta plus 1 IB. So it will what will become? VCC, IB RB, VBE minus IE will replace by beta plus 1 IB into RE. Okay, then we will collect all the IB term at one side and rest of the voltages to other side. It means VCC minus VBE, that is the at the right side, which is nothing but these two will come to the other side. IB will take in common. So RB plus beta plus 1 IB, because these two are negative terms, they will move to the right side, will become positive, and these two, one is positive, one is negative, it is same. So my base current IB, which is nothing but VCC minus VBE upon RB plus beta plus 1 RB. Okay, if you remember in a fixed bias configuration, what we got? Our IB, which is nothing but VCC minus VBE upon only RB. But as this emitter resistor came into the picture, and across which a current of IE is flowing, and IE, which is nothing but beta plus 1 IB, that's why the beta plus 1 RE, this term came into picture. Beta plus 1 for this IB in IE in terms of IB, and this RE is for the emitter resistor. So it is easy to remember with comparing the fixed bias configuration. This is the IB equal to VCC minus VB upon RB in fixed bias configuration, but in emitter bias configuration only addition of beta plus 1 RE. RE, why it is added? Because it is in a loop. In this loop, RE is in series connection of with RB. That's why RB plus RE. Why beta plus 1? Because of this IE current. Okay. Then, similar to the fixed bias configuration, here also we will find that the resistor RE, that is reflected back to the input base circuit by a vector of beta plus 1. That's the same thing that I told, that our RE will reflect back with the base side with a factor of beta plus 1. Okay. Then we will see the collector emitter loop, that is our output loop. So you can see from here, it looks like a VCC, RC, a voltage across this, which is nothing but VCE, then RE, then ground. So here also same, VCC, RC, VCE, RE and ground. It is grounded. So I will move like this. I will write a loop equation. What it will become? Negative to positive. VCC. Then a current that is flowing IC across the RC. A current IC is flowing. That means IC RC. This is the current direction IC, because it will move like this. So minus IC RC. Then plus minus VCE, which is nothing but minus VCE. Then a current IE is flowing RE. So IE RE equal to 0. Okay. So we know our IB range is in microampere. Our base current, that is in microampere range. IC and IE both are in milliampere range. And I told earlier that our these two current are almost approximate to same. We know that our IE, which is nothing but IC plus IB. But as this value is very less, let's take this is 0.5 milliampere. Let's take this is 0.4 milliampere. And this is nothing but 2 microampere. So if I will combine 0.4 milliampere plus 2 microampere, 2 microampere means 0.002 milliampere. Okay. And it is 0.4 milliampere. If you will add these two, what it will become? 0.402 milliampere. So this 0.402 almost approximate to 0.4. So in some case for our calculation part, we can neglect this value of IB. As this value IB is approximate to 0, we can neglect. Means we can take approximate this IB as 0. Then what it will become? My IC will become, IE will become IC. It is not almost equal, but approximate to IC, both are equal, IC and IE. So here I can take in place of IE, I will replace it by IC. So it will become VCC minus ICRC minus VCE minus ICRE equal to 0. Then I have to find for output side what I need to find? VCE. For input side I have to find IB. Okay. So everywhere you will see the input side I will find IB, and at the output side I will see VCE according to our configuration. So our VCE is nothing but VCC, and this two term multiplied with the current IC. Okay. So once we will find the value of VCE, then it will become easy to calculate other thing. You see, we know this is in previous case, in fixed bias case, our emitter was grounded. That's why my VE value was 0. But here the emitter is not grounded, because this is the emitter terminal. With the emitter terminal, resistor RE is connected. Then what will become my emitter voltage? This VE, it means from the emitter to ground. This is emitter terminal. From emitter to ground, this voltage is VE, and which is nothing but IE into RE, because the current across it and the resistor across it, that is IE RE. So once we found the value of VE, then from here we know VC equal to VC minus VE. So what will become VC? Our VC is nothing but VCE plus VE. We know value of VE, we know value of VCC, we can find the VC current. Means the collector current. Collector voltage means VC, that is collector voltage. It means from the collector terminal to ground. Every time when I am writing a single notation, VC, VE, VB, everywhere, that is from that terminal to ground. And VCE, that is between two terminal, collector to emitter. VBE, between base to emitter. Okay. So our VC, which is nothing but VCE plus VE. So that is, you can see our VC in this case, what is our VC? This is the collector terminal. So this is the collector terminal, which is nothing but across which a resistor RC is connected and a voltage source VCC is connected. This is the collector terminal. So from here to ground, the voltage, which is nothing but that a current flowing IC. So if I write VCC minus ICRC, this is grounded, means minus VC equal to 0. So VCC minus ICRC equal to VC. Okay. So easily from there I can find the value of VC and if I need for the VCE also. Similarly, we can find the value of VB also, VCC minus IBRB. For the input loop, this is VCC minus IBRB. You can see from here, this is the base voltage. Okay, this is the base voltage. So if I write the loop equation for the base, from base to a resistor RB with a voltage VCC. So if I write a loop like this, VCC minus a current IB is flowing, minus IBRB minus VB equal to 0, because I am measuring a voltage VB, means from base to ground, that is VB. So VCC minus IBRB, that is equal to my VB. Okay. So similarly, we found the value of VB, and we know VE, we know VB, so we can find VB also if you need. Okay. Then the third one is nothing but the saturation level. Similar to the fixed bias condition, what is the saturation level? This is the maximum collector current or maximum output current at saturation level. So this is the saturation level. You can see in the previous fixed bias configuration. So this is the saturation level, means at the edge of saturation level, what is the maximum collector current that occurs, and that at that value my VC is nothing but VC is sat. So here also similar to the previous one, here the VC IC sat, which is nothing but VCC upon RC plus RE. In previous case, it was only VCC upon RC, because there was no RE. So here, as the RE came into picture, because emitter resistor, we can add that RE. So it will become VCC upon RC plus RE. Okay. So but here the emitter saturation current for across the collector for emitter bias will be less than for the fixed bias, because of this addition term RE, that will decrease my IC. Let's take VCC 10, this is 2. So 10 by 2 equal to 5 for my fixed bias configuration. But now it is 10 plus 2 plus, let's take another 2. So 10 by 4 means 2.5. Before it was 5 milliampere. Now it is 2.5 milliampere. It means IC sat for fixed such emitter bias is less as compared to the fixed bias configuration. Okay. Now the load line analysis. What is load line? That is, it is a line which connect on the characteristic graph to find a Q point, and this how to find this load line in the output equation. In this equation, if we will put a value of IC equal to 0, that is for one axis, and VC equal to 0 for another axis, we will find the two values. You see, if I will put in this equation, if I will put my IC equal to 0, then my VCE, which will become VCC. So that I found my VCE is equal to VCC, and this is the point VCE equal to VCC. In the second part, if I will make my IC VC equal to 0, then what will become IC? IC is nothing but VCC upon RCRE. So IC will become VCC by RCRE. In fixed bias, it was VCC upon RC only. But as the addition of RE came into picture, the RE added. Every time you compare both any bias you are studying, starting from the fixed bias, emitter bias, voltage divider bias, you can compare each and every one, so that it will become easy for you to remember. So this is VCC upon RCRE. So this is the four thing that all have completed. One is base emitter loop. Second one is the collector emitter loop. Okay, base emitter loop, the base current which is nothing but VCC minus VB upon RB plus beta plus 1 RE. Remember this equation. Collector emitter loop, VCE which is equal to VCC minus IC upon RC plus RE. And the saturation current, that is, this is the saturation current which is nothing but VCC upon RC plus RE. And at the load line, these are the 2 points. Once I find this 2 point, I can join a line, and from that point I can find my Q point with a fixed value of IB. Okay. Now let's see one numerical based upon this emitter bias configuration. So it is a question that is given. Draw the load line for the network of this circuit. Okay. For this we have to draw the load line, the characteristic for the transistor. Okay, from the diagram, first of all, you see whether which type of biasing is this. It is a emitter bias configuration, because a RE is connected across the resistor. It means a RB RC was there for fixed bias, and addition of RE in emitter side will give me the emitter bias configuration. So it is asked, draw the load line for this network on the characteristic for the transistor. So this is the characteristic graph given, IC versus VC value. We have to draw a load line. So now tell me, for drawing a load line, what are the things that I should know? We should know the equation, and for the emitter bias configuration, what is the load line equation for the output characteristic configuration, which is nothing but VCE is equal to VCC minus IC into RC plus RE. Or indirectly I can say, for my load line, when my IC equal to 0, my VC is nothing but VCE, which is nothing but VCC when IC equal to 0, and my IC my IC which is nothing but VCC upon RC plus RE, and when my VC equal to 0. If I will find these 2 points, then only I can make a load line. Now in this question the VCC is given 18 volt. It means my VC value is nothing but 18 volt. Okay. Now my IC is nothing but VCC upon RC plus RE, and in the diagram it is given the value of RE which is nothing but 1 kilo ohm. So 18 volt divided by 1.1 kilo ohm, that is RE, plus RC is nothing but 2.2 kilo ohm. So we will find 18 upon 3.3. So 3 5 3 is 18, 6 3 is 15. So it is nearly equal to 5 point something. Okay, 5 point something milliampere. You have to see that IC value that we found 5 point something milliampere, and the VC value is nothing but 18 volt. So in the characteristic graph I will draw a line with a current is nothing but 5 point something milliampere somewhere in between this, in between 5 and 6, and a voltage of 18 volt, that is somewhere between 15 to 820. So once I found these two values, I will join these two values. So what I will get? I will get the load line. That is for the first half it is given. Okay, so this is the load line. Now in the second part it is asked for a Q point at the intersection of load line with IB equal to 15 microampere. Means it is given for you that this is the IB values, different value IB 0, 5, 10. This is IB equal to 15 microampere. Remember IB is always in microampere range. So this is the Q point. Okay, for a Q point means it is the Q point at the intersection of IB load line. Find the value of ICQ and VCEQ. Okay, once we found this value, this is the point on this Q point, then we can easily draw into the two axes. So as we will draw on this point on the two axes, it will touch a value somewhere in between 3 and 4, that is nothing but 3.2, 3.3 a value, and in the VC axis that will touch a value in between 5 and 10, which is nothing but, let's take this is 7.5. So in between a half value, so 5 and 10 is nothing but 3.5, and this value touches nearly 3, so let's take 3.2 or 3.3. So it is asked what is the value of ICQ and VCEQ. Our ICQ which is nothing but 3.3, our VCEQ which is nothing but 7.5. This ICQ and VCQ, what does it mean? It is the collector current and collector to emitter voltage at Q point. Okay, that's why at Q point I am finding this is the IC value, this is the VCE value. It is not that saturation value. It is not like that. It is the point on the it is the axis on the Q point touching both the axes, both IC and VCE. Okay, then the next part it is asked what is the beta DC. Beta DC means it is the common, it is our emitter configuration. So common emitter configuration, we have to find the beta. And what is the formula for beta? At Q point it is asked beta DC at Q point. So means at this point we have to find the beta. So our beta DC which is nothing but ICQ at Q point upon IBQ. Okay, so IC value that we found from here, ICQ which is nothing but some ICQ, that is 3.3 or 3.2 or 3.3, and IBQ. And what is the value IB is given? IB value that is given 15 microampere. So you will put 15 microampere. So you will get a value of beta DC. Okay, so in the next part, fourth part, it is asked using a beta DC calculate the required RB. We have to find the value of RB because in the question the RB value is not set. So we know in our IB equation, what is our IB equation? Our IB equation is nothing but VCC minus VBE upon RB plus beta plus 1 RE. From the input loop you can see this is the IB equation, VCC minus VBE upon RB plus beta plus 1 RE. Okay, from here what we know, I know the value of VCC is nothing but 18 volt. It is given in the question. VBE value is always, means in question it is 0.7 volt, 0.7 volt always, divided by RB value that we have to find. Beta value is given in this question. You can see the beta value that we found from here 3.3 upon 15 microampere. Whatever the value that you will get, you will put that value of beta. Okay, from here then beta plus 1 multiplied by RE. RE is given 1.1 kilo, and we know IB value is given 15 microampere. So we know IB, we know VC, we know VB, we know everything except RB. Okay, so our if we solve this one, I will get a RB value. If you solve this one, you know everything. This 18 minus 17, which is nothing but 17.3 divided by this is 15 minus beta plus 1 RE. You know everything. You can find the value of RB. Okay. So this is all about your emitter bias configuration. In the next class, we will see the voltage divider configuration.